I wasn't. I take your notes. Because no
All right, this is going to be a relatively short day because we just have this last page to go over from the section. Tomorrow we're going to have a free response day, which kind of is going to highlight some of these antiderivatives and integrals that we've been working with. So just kind of extra practice tomorrow. This is by no means going to take the entire period, so you will have plenty of time towards the end of today to work on some homework problems, ask questions, whatever you have to do. Okay. So yesterday we were looking at the fundamental theorem of calculus, which basically told us a strategy or a method to calculate the area under a curve by hand using some calculus. So we didn't have to go through those tedious rectangles or trapezoids or any of those geometric shapes. Okay, we were just able to kind of use calculus to our advantage. And we looked at equations yesterday in terms of some examples, but today we're going to take a look at a table format, just a different kind of piece of information that we have available to us. So how might the fundamental theorem work in this case? Okay, we're just going to explore that idea today. So the table shows values of a function, f of x, and its first and second derivative values at some different locations. Okay, use the information to answer the following questions. So if we look at 1, it's asking what is the value of the integral from -3 to 1 of the first derivative. So graphically, we're trying to figure out what is the area under the first derivative graph from -3 to 1. But we don't have the graph available to us to kind of estimate what it might be. So we might have to use some table values here to help us out. So this is where the fundamental theorem of calculus is going to help us. If we think about the process from yesterday, we first have to work backwards, okay, find an antiderivative. So if the function we're starting with is a first derivative, what would the antiderivative be if you work backwards? The original, which would be f of x, okay? And typically, we would write plus c, like we did in a previous section, but did we discuss yesterday why that is sometimes not necessary? When you have bounds, okay? And notice how we do here, okay? So you don't need to put the plus c. We will, however, write the bracket and rewrite the bounds. Okay, so we worked backwards from the function. We're now going to evaluate it at the bounds. Which bound do we plug in first? The top, okay? So this is going to be f of 1, and then we have to subtract what we get when we plug in the bottom, which would be f of -3. Do we have those values available to us? Yes, okay, because we have a table. Let's see, f of 1 is -2, and now we have to subtract f of -3, which is 4. So overall, we'll get -6. All right, so ultimately, we're now able to say that the area under the first derivative graph from -3 to 1 is -6. What's that -6 telling us? All of it?
More. 6 more units below the x-axis.
There's 6 more squared units below the x-axis than there is above. Okay, so we have more area underneath the x-axis than we do above. We don't have a graph to confirm that, but from yesterday we kind of had those connections that we were able to see based off the examples. Okay, let's go ahead and try 2. What is the value from -1 to 3, but this time we're kind of amping it up. We want to look at the combined area under the first derivative graph and the second. Okay, we don't have the graphs available to us, we just have a table, so somehow we have to be able to use these values to our advantage. So according to the fundamental theorem of calculus, we're first going to work backwards and then we'll plug in those bounds. Okay, top minus bottom. So if we work backwards from a first derivative, what would we have? The original function. Okay? And then we're going to work backwards from a second derivative, which would be the first derivative. Okay, an antiderivative. We're working backwards. Notice how we have the bounds, so we do not need the plus c. We will now throw in the bracket and rewrite -1 and 3. All right, so if we check this out, we first have to plug in 3 into all the x's and then subtract what we get when we plug in -1 in for all those x's. So if I plug in 3, f of 3 is 1. And if I plug in 3 for the derivative, I'll get 3. We then have to subtract what we get when we plug in -1. So f of -1 is 0. The derivative at -1 is 1. So it looks like we have 4 minus 1, which is 3. So our combined area under each of these curves is 3. So we have more combined area above the x-axis than we do below, even though we don't have a graph available to us. We doing okay? Does it seem pretty simple? I'm hoping. Okay. This, in my opinion, this is a little bit more simple, or a more simple example of the fundamental theorem than what we did yesterday, because we physically had to work backwards using shortcuts like the reverse power rule or a trig function. That is a little bit more demanding mentally, I think, than this, because we can plug in numbers from the table. Okay, so this is still a similar concept to what we did yesterday, just we have a different piece of information available to us. Instead of having an equation, we have a table. All right, what about 3? The area underneath the 3 times the second derivative graph, whatever that would look like, from 1 to 5. Can we work backwards? Can we work backwards from a first derivative, or sorry, a second derivative? I'm going to say first derivative. I know. I made a little oopsie. So if you are starting with a second derivative and you want to work backwards, that means you previously had a first derivative. What's going to happen to the 3, though? Can we make an educated guess? It's going to stay there. Yep. Just like we keep coefficients when we do derivatives. For instance, if I had 3 sine of x, the derivative would be 3 cosine of x. Okay, just like you keep coefficients for derivatives, you can keep coefficients for integrals. Okay, antiderivatives. We don't need the plus c because we have the bounds, so we'll throw in the bracket and go from there. All right, so we're going to plug in 5 first. The first derivative at 5 is 2. So I need 3 times 2. And then I'm going to subtract what I get when I plug in the bottom bound of 1. Which would be 0. So 3 times 0. So in the end we get 6. Bless you. Okay, a positive result, we have more area above the x-axis than we do below. Do you guys think you can try the next one? Yeah? It's kind of a merger of 2 and 3 together, because we have multiple functions, but we still have coefficients. So see if you can do that one. 4.5? Oh, sorry, 8.5. My bad. My bad. The last number I looked at was this 4, like when I got done doing everything, and that's the number I wrote down. 8.5 better? Yeah? Do we gotta go over any part of that? Yeah?
Why is it 2 times 3 in the first one?
This one right here?
Yeah.
Okay, so
Where did the 3 come from?
this 2 came from that coefficient.
Yeah.
If I plug in 3 into the first derivative,
Oh.
that gives me 3.
Okay.
Okay. All right, so far so good? Yeah? Oh. It happens. It happens. Top minus bottom. All right, let's try 5. What's the equation? Oh, this is a throwback. What's the equation of a tangent line at x equals 3? What do we need to know? Point, slope. All right, so they want it to be the equation of the tangent line to the graph of f. Okay, that's pretty important. We have to know which function we're dealing with. So the point value should come from f, and the slope value is going to come from where? F prime. All right, so based off the table, f of 3 is 1. F prime of 3 is 3. Equation of the tangent line, y minus 1 equals 3 times x minus 3. That's too simple. Okay, we're gonna do another one.
No, we can leave it at that, honestly.
Oh, we're gonna leave that one like that, but we're gonna do another one. What if it said graph of f prime at x equals 3? Okay, we're still going to write the equation of a tangent line, but this time it's on the derivative graph and not the original. Can we think about how that would change perhaps our calculation? There we go. It's the same thing. We're just using different functions. So the point value comes from the derivative, but the slope is going to come from the double prime, the second derivative. Okay, so based off the table, f prime of 3 is 3. The second derivative value is negative 3. So y minus 3 equals negative 3 times x minus 3. There's a whole bunch of 3's. Each 3, though, means something different. All right, so moral of the story, we have to be careful as to which function we're actually using to draw the tangent line on. We're used to using like an f and an f prime, but notice how we can switch it into an f prime and an f double prime. Okay, it's the same concept, just utilizing a different function. All right, let's try the last one. Use the equation of the tangent line in number 5, so that's this first one that we did, to approximate the value of f of 3.1. Is this an over or an under estimate? So how do you think we can use this tangent line to make an approximation for a value? There we go. All right, so no calculator, we can do this. 3.1 minus 3.1 times 3.3. Add the 1, 1.3. Okay, so be careful, okay, not to leave your final answer as y equals 1.3. This is an approximation. You have to use the squiggles. So f of 3.1 is approximately 1.3. Is this an over or an underestimate to the actual value? You have an idea? Yeah.
I'm saying over.
Why?
Because f double primes is negative, so f prime is concave down.
Okay, so how did you know the second derivative is negative? Where were you looking at in the table at the top?
I sheet. We don't have 3.1.
We don't have 3.1, but we do have...
But f of 3 and f of 5 are both negative.
Okay, notice how 3.1 is between 3 and 5 in the table. Okay, both these values are negative. What if the 5, though, was positive?
Not enough information.
Yeah, not enough against it.
You can.
Still an over because it's tangent to f equals 3.
Okay, notice how we use this tangent line equation to help us get this approximation. And this tangent line equation was centered or used at the x value of 3. So we can use this, okay? So it's still over. Okay, so we'll say since the second derivative at 3 is negative, what does that tell us? If a second derivative is negative, then
f of x is concave down.
f of x is concave down.
Therefore,
So the tangent line
is an over.
is an over approximation. Okay, because if you have a concave down graph, a tangent line, no matter where you draw it, will always be above. How are we doing?
Good.
Pretty good. All right, that's it for this section. We're going to have our free response day tomorrow for extra practice, but you can utilize the rest of today for some homework time.